Hello, and welcome to AI for Mechanical Engineering. So far in this lecture, we've covered some basic concepts in linear algebra. Today, we'll be looking at another core mathematical concept in machine learning, optimization. Now, optimization refers to the process of making something such as a system, process, or even a decision better. Now, optimization has been an important tool in a lot of disciplines such as engineering problem solving or decision science. As a matter of fact, humans optimize all of the time. For instance, if we're traveling from one point to another, we tend to find the most efficient or the fastest way to get there. Nature as well optimizes. For instance, if you look at the way trees grow, they tend to grow in a direction that maximizes their chances of survival. So here's an example of how people can optimize when making decisions. Let's consider a case where a person is drowning in the sea, and our objective as a lifeguard is to save that drowning person. Here we have three possible choices, or three possible routes, A, B, and C, and we have to determine which path is the best in terms of saving that person. Now, all three choices can be seen as optimal choices, depending on how you set up your objective. So for instance, if we're simply trying to minimize the distance between the rescuee and ourselves, A would be the best or optimal route. So case 1, minimize distance. Now in a more realistic case, we want to get to the person as fast as possible. So in this case, we want to minimize the time that it takes to get to that person. Now the time that it would take for us to get to that person would simply depend on the speed at which we travel in the water or on the sand. So depending on how fast you can swim or how slow you can run, B or C can both be an optimal choice in case 2. So to summarize, the best decision or the optimal choice depends on the objective of the problem. Now another example in nature can be seen when we look at the way light refracts through different medium. So for instance, let's say this is air and this is water. You notice how the light refracts through a different medium. Now this can all be seen as some sort of an optimization. Another example can be seen when we look at the way ants travel through different surfaces. So for example, if we assume that there is a food source along this point, and the ants can travel a lot faster throughout this portion, their goal would be to get to the food as fast as possible, meaning that they would try to minimize this distance. So these are all examples of optimization in nature. So to formulate an optimization problem, we have to keep in mind that there are three key components. Now the first part is the objective function, which tells us what the goal of the problem is. The second part is the decision variable, or unknowns. So these are the values that we are able to change in order to achieve that goal. And finally, we have the constraints, which basically tell us what we have to consider in the optimization problem. And if we have these three components defined, we can then use the following procedures. So first of all, we have to identify the objective function, variables, and constraints for a given problem, which is known as the modeling phase of the optimization process. And once we have a formulation of the model, we can then deploy some optimization algorithm to actually solve the problem. So to find the solutions. Now in this course, instead of focusing on the different types of optimization algorithms, we'll be focusing more on how we can formulate different optimization problems in order to train machine learning models. Then let's take a look at a mathematical formulation of an optimization problem. So first of all, we have the three components that I've described in the previous slide: the objective, design variables, and constraints. Here, the decision variable does not refer to a single value, but rather an n-dimensional vector containing the individual components of each design variable. Next, the objective function is a function that maps our design variables to some value which essentially lets us know how well we are doing with respect to the goal of the problem. And finally, we have our feasible region, which is determined by the constraints that we have defined. And once we have all these components defined, we can finally solve for the optimization problem. Now the solution here is considered the optimal solution, denoted as x star, and we can say that x star is an optimal solution if it belongs to the feasible region, and the value of the objective function is always less than all values of x that belong in the feasible region. So this shows a basic mathematical setup for an optimization problem. Now if we look at an alternative representation of the same optimization problem, we can have the following. So instead of minimizing, if we want to maximize the objective function, we can simply flip the problem by adding a minus sign in front of the objective function. In other words, minimizing this function would be equivalent to finding the maximum of this function, which essentially is a flipped version of the function above. The same can be said for inequality constraints, where we have some constraint that is less than or equal to 0. We can represent it as being greater than or equal to 0 by adding this minus sign here. And finally, for inequality constraints, we can represent it as a combination of two inequality constraints. So these are all alternative representations of the same mathematical formulation. So in summary, we've looked at different ways to both conceptually and mathematically formulate optimization problems. Now, if you look at the different types of optimization problems, you can see that we have the unconstrained and the constrained optimization problem. So for the first case, in the unconstrained case, we do not have any constraints, simply implying that our objective is to minimize the objective function with respect to the design variables. Now in the second or constrained case, we have a set of constraints, both inequality constraints or equality constraints, that define the feasible region of the optimization problem. So in the second case, our goal is to minimize the objective function with respect to the design variables that exist within the feasible region. Now in terms of the topics that we've learned in previous lectures, we can find examples for each of these optimization problems. In the first case, one example would be the least squares problem, where the goal was to minimize ax minus b without any constraints. In the second case, we can think of the least norm solution, where the goal was to minimize the norm of x subject to the following constraints. And if we graphically represent this, we have the following. Next, we have convex versus non-convex problems. Now, I'll be talking about this in detail later on, and although this is not, I'm emphasizing that this is not the formal definition of a convex problem. To put this very simply, we can determine whether the optimization problem is convex or not by looking at the shape of the objective function. So for instance, if f of x looks like this, then we can call it convex. Whereas if f of x has some arbitrary shape, in this case, we call this a non-convex optimization problem. Now again, this is not the official way to determine whether an optimization problem is convex or not, but I've shown you this concept just to give you an idea of what convex or non-convex problems look like. Now the key takeaway here is that convex properties make it so much easier for us to solve optimization problems. Therefore, in this lecture, we'll be mostly reviewing topics in convex optimization problems. Now, let me formally define what a convex optimization problem is. So first of all, we can say an optimization problem is convex if the objective function is a convex function. So this is our first requirement. And second, the feasible region as well as a convex set. And the reason why I said convex properties make it so much easier for us to solve optimization problems is because all solutions or local solutions can be seen as global solutions. So in other words, if we find a local optimum, we have guarantee that we have found the global optimum, or simply the best choice among all possible choices. If we try to visualize this, a non-convex case would look something like this, where all of these points can be seen as local minimums. However, for a convex case, once we find a local optimum, we have guarantee that this is the global solution, or the global optimum. So this is a conceptual description of what a convex optimization problem looks like, but how do we define what convex is? In order to formally define what convex implies, we first have to recall or review how we can represent linear interpolation. Here, for two given vectors, x and y, any point along this line can be represented as z, where z consists of a linear combination of x and y with weights that add up to 1. So in other words, z can be represented as alpha x plus beta y, where alpha and beta add up to 1. Another representation can be the following. So let's say we have two vectors in a one-dimensional space, x and y. Now if we try a simple case, 1 over 2 times x plus y, we end up with this point, which corresponds to the center of x and y. If we change this slightly and look at a case where we have 1 over 3x plus 2 over 3y, this time you notice that we end up with this point over here. So if we collect all the possible coefficients that add up to 1, we simply have a collection of these points along this line, or in other words, the linear interpolation. So based on this representation of linear interpolation, we can define what a convex function or convex set is. Starting with the convex function, here let's assume that we select two arbitrary points along the function. If we draw a straight line through these 2 points, in other words, find the linear interpolation, a function is convex if all points of that function exist below that linear interpolation. If we mathematically represent this, we can say that the linear interpolation of these 2 points is always greater than or equal to the values of those points along the function. Now, if we look at the convex set case, a set is considered to be convex if the linear interpolation between 2 arbitrary points also exists within that set. So if we graphically represent this, regardless of which points we choose, the linear interpolation of any 2 points will always exist within the set if the set is considered to be convex. However, if we have a non-convex set, we will end up with points that do not exist within the set, implying that we have a non-convex set. And if we mathematically represent this, we can have the following, where the linear interpolation between x and y, or 2 arbitrary points within the set, falls in the same set, then we can conclude that we have a convex set. So in today's lecture, we've covered some important concepts regarding how to set up an optimization problem and some important definitions and properties that we need to know in order to solve optimization problems. This is the end of today's lecture, and thank you.